The transformer model has revolutionized natural language processing by introducing the power of attention mechanisms to neural network. And this groundbreaking architecture has become the backbone of many state-of-art NLP models, from machine translation to text generation. In this video, we will provide a comprehensive introduction to the transformer models, discussing the key concepts and components that make them so powerful. So let's get started with what is a transformer model. Basically, transformer is a popular and powerful deep learning architecture used in natural language processing. It is particularly effective for tasks like language translation, text summarization, and question answering. At a high level, the transformer is a neural network designed to process sequential data such as text by using a combination of self-attention mechanism and feed-forward neural networks. And this architecture is organized into encoder and decoder components. First comes self-attention. Now, self-attention is the technique that allows the transformers to efficiently process and attend to different parts of the input sequence simultaneously. And this enables the model to learn contextual relation between the words in a sentence, making it well suited for NLP tasks. Then comes encoder and decoder. Now, encoder takes in the input sequence, example a sentence, and encodes it into a continuous representation. The decoder then decodes this representation to generate the output sequence, say a translated sentence. Then comes feed-forward neural networks. Now, this transformer uses a simple feed-forward neural network architecture for its internal computation, and these networks are composed of fully connected layers with activation functions such as rectified linear unit. The transformer's strength lies in its ability to process the input sequence in parallel, making it significantly faster and more efficient than previous sequential models such as recurrent neural networks and long short-term memory networks. And this parallelization also allows the transformers to be trained on increasingly large and complex datasets, resulting in state-of-art performance in various NLP tasks. So to summarize this, we can say transformer is a powerful neural network architecture designed for natural language processing tasks. It uses self-attention mechanism to efficiently process sequential data and feed forward neural network for internal computations, resulting in a highly effective and efficient model for NLP. Then comes the architecture of transformer. Basically, the transformer architecture uses a key value mechanism within its self-attention sublayers, and this mechanism helps the model efficiently learn contextual relations between the words in a sentence. So let's break down the transformer architecture using the key, query, and value terms. First, it has input embeddings. That is, the input sequence or a sentence is first converted into a sequence of numerical representation using an embedding layer. And this embedding layer converts each word in the sentence into a dense fixed length vector. Then comes key, query, and value vectors. So for each word in the input sequence, three separate fixed length vectors known as the key, query, and value vectors are generated. These vectors are derived from the input embedding using linear transformation. Then comes self-attention mechanism. Now, self-attention mechanism computes a weighted sum of the value vectors based on the similarity between the query vector and the key vector. And this allows the model to selectively attend to different parts of input sequences when computing the representation for each word. Then comes attention score. Now, to compute the attention weights, the dot product of query vector and transposed key vectors is calculated. Then a softmax function is applied to obtain the attention weights. Then comes attention values. Now, attention weights are multiplied element wise with the corresponding value vectors, resulting in a weighted sum of the value vectors. Now, this weighted sum represents the learned representation of input word, taking into account the contextual information from the other words in the sequences. Then positional encoding. To inform the transformer about the relative or absolute position of the words in input sequence, positional encoding is added to the input embeddings and the internal representation produced by the encoder and decoder. This allows the model to learn positional information and maintain the order of words. Then feed-forward neural networks. So after the self-attention sublayer, a position-wise feed-forward neural network is applied to each position in the input sequence separately. And this network consists of two fully connected layers with a ReLU activation in between. This feed-forward network helps the model learn contextual information. And finally, we have an output layer. That is the final layer of the encoder or decoder applies a linear transformation and a softmax activation to generate the output probabilities for each possible output symbol, example, characters or words. So to summarize this, we can say the transformer architecture uses a self-attention mechanism with key, query and value vectors to efficiently learn contextual relations between the words in a sentence. Now the model computes attention weights based on the similarity between the query and key vectors, allowing it to selectively attend to different parts of the input sequence when computing the representation for each word. And this key value mechanism is a powerful tool in the transformers architecture, making it highly effective for natural language processing tasks. Thank you.